Hi guys, this is Dr. G here, and in this video we are going to talk about the atom. And please note that I have published a previous video on elements, and I highly recommend you to watch that video before reviewing this particular video on the atom. Okay, so let's talk about the atom. So what is an atom? So atom is basically the small particles, okay, the small particles that elements are made up of, or you can say the elements that you see listed on the periodic table are made up of small particles called atoms. And the thing about these atoms is that one element contains only one type of an atom. Okay, so basically the atom is the smallest particle of an element that retains the characteristics of that particular element. Okay, elements are the way they are chemically or physically because of their smallest particles called atoms. So in this in this figure I have in this slide, I have three different elements: copper, carbon and helium. Okay, of course you can see copper and carbon, but you couldn't see helium to your naked eye. But when you take a piece of copper or carbon, okay, that piece of copper or carbon is made up of either copper or carbon respectively, elemental copper or elemental carbon respectively, and these elements are made up of small particles called atoms. And in here I have, or in this figure they have graphically shown you the atoms. I mean, you can imagine that the spherical structures that you see are the atoms, even though that is a false representation. Atoms are not like, you know, these spherical structures, but anyway, you can say that every element is made up of one type of a small particle called atoms, and then their properties are dependent on these smallest particles. And when it comes to helium, once again, even though you couldn't see helium to your naked eye, if you take a helium balloon, okay, inside that balloon you have helium gas particles, helium gas particles, and these helium elements or helium particles are made up of smallest particles called atoms. Okay, that is a brief introduction to atoms. So basically, what are atoms? They are the smallest particles of an element, and these particles retain the chemical and physical characteristics of that particular element. And to understand the concept called atom in more detail, we can go into history. Okay, we can talk about the atomic theory that Dalton proposed in the 1800s, which is of course more than 200 years ago, but still his explanation of an atom using the atomic theory still holds true to some extent in today's world. Okay, so even though this Dalton's atomic theory is more than 200 years old, this theory can still be used to understand the basic characteristics of an atom. Okay, once again, all these may not be true 100% of the times, but I mean, still it can shed light into the concept of atoms. Okay, and Dalton's atomic theory can be understood in four different parts. Okay, the first bullet point, or the first part of Dalton's atomic theory, is that all matter is made of atoms. Okay, basically atoms are invisible and they are indestructible. Okay, so all matter is made up of atoms and they are invisible and they are indestructible. Okay, that is the first part. And the second part is that all atoms of a given element are identical in mass and properties. Third part of atomic theory is compounds are formed by a combination of two or more different kind of atoms. Okay, and then the last part of Dalton's atomic theory is that a chemical reaction is an arrangement of atoms. And here's the thing. Modern atomic theory is of course a little more involved than Dalton's theory, but the essence of Dalton's theory remains valid, okay? And today we know that atoms can be destroyed via nuclear reactions, but not by chemical reactions. Also, there are different kinds of atoms, okay? Or you can say when you take an element, you have atoms of that elements with different masses. We call them isotopes. Okay, isotopes are also atoms of the same element, even though they have different masses. Okay, so they are not identical. Isotopes are not identical, um, but still they are atoms of the same element. Okay, so once again, guys, even though modern atomic theory is a little more involved than Dalton's atomic theory, which is more than 200 years old, the essence of Dalton's atomic theory remains valid. Okay, so these four bullet points basically explains or summarizes Dalton's atomic theory nicely, and we can understand what is an atom by going through these four bullet points. Okay. All right. So next, what we are going to talk about is the parts of atom. Okay. So if you remember a couple of slides ago, okay, atoms were represented by spherical structures, right? So I mean, this was a good way to represent atoms, of course, when you first introduce the concept atom. Okay, so you want to make sure that people understand this graphite is made up of one type of particles, and those particles are identical, and we call them carbon atoms. Okay, so that is why they use these black spherical structures to represent carbon atoms, right? So in this slide we are going to actually talk about atom in more detail, or the structure of an atom in more detail, and when you learn about the parts of atom, you will realize that atoms are not solid spheres. Okay, atoms are not solid spheres. Instead, they have a more dynamic structure. They are not just spherical structures, they have a more dynamic structure. Okay, so let's talk about the atomic structure. So to talk about the atomic structure, we have to talk about parts of atom. Okay, so atoms are made up of three subatomic particles. Atoms are made up of three subatomic particles. We call them proton, neutrons, and electrons. Okay, so atoms are made up of three subatomic particles called protons, neutrons, and electrons. Okay, so let's talk about protons first. Okay, so we have three different subatomic particles, protons, neutrons, and electrons. And protons are positively charged. Okay, neutrons are neutral, and electrons are negatively charged. Okay, so when it comes to charge, protons are positive, neutrons are neutral, let's call it 0, no charge, and electrons are negatively charged. And the other important thing is, out of these three subatomic particles, two subatomic particles are heavy. And the remaining subatomic particle is very light. Okay, how light? It is actually approximately 10,000 times lighter than the heavier subatomic particles. Okay, so you can say protons and neutrons are 10,000 times heavier than electrons. Okay, so protons and neutrons are heavy and electrons are light. Okay, they are very light. And let's talk about the mass of these heavy neutrons and protons. Okay, let's talk about the mass of these neutrons and protons. Of course, you feel like, you know, they're very 10,000 times heavy, so they should have some good masses, right? So basically, as I mentioned earlier, neutrons and protons, they are heavy, and their masses, mass of a proton is approximately equal to the mass of an electron. Mass of a proton is approximately equal to mass, not an electron, I'm sorry. Mass of a proton is approximately equal to mass of a neutron. Okay, and this mass is around 1.7 times 10 to the power minus 24 grams. Okay, so even though protons and neutrons are the heavier subatomic particles, their mass is not that high. Okay, their mass is not that high. It is approximately 1.7 times 10 to the power minus 24 grams. Minus 24 grams. That means, it is a very small mass. Okay, 1 gram is a very small entity. 1 gram is a very small entity. Few sugar grains, maybe a couple of sugar grains will be 1 gram. Okay, not couple, maybe a few sugar grains will be 1 gram. Okay, so to have a minus 24 factor into the mass of a neutron or a proton, they are very tiny. Okay, even lighter than very tiny dust particles that we could barely see. So this is how lightweight these subatomic particles, and of course the mass of a electron, it is 10,000 times lighter. Mass of an electron is 10,000 times lighter, and the mass of an electron is around 9.1 times 10 to the power minus 28 grams. Minus 28 grams. Okay, much lighter. Okay, electron masses are much lighter. Okay, so that's the mass. Okay, that's the mass of protons, neutrons, and electrons. Okay, protons, neutrons, and electrons. Mass of a proton is approximately equal to the mass of a neutron. Okay, so these are the two heavy subatomic particles, and then the mass of an electron is approximately 10,000 times lighter. Okay, so we are talking about very tiny particles. Very tiny particles. Okay, and here's the thing. So you have 3 subatomic particles in an atom. Okay, 2 are heavy and 1 is 10,000 times lighter. So when you consider how they are arranged in an atom, okay, this is how it happens. Okay, the 2 heavy particles, protons and neutrons, they are the heavy guys, right? So protons and neutrons, they are very heavy, so they are not very mobile, as you can assume. It like a very huge or enormous human being. Okay, when you are very big, your mobility is very small. Okay, very small. So basically protons and neutrons are practically immobile as compared to electrons, which are much lighter, 10,000 times lighter in weight or mass. Okay, so basically because of that, the protons and neutrons are centered around an area called the nucleus. Okay, in an atom, protons and neutrons are centered around a small area called the nucleus. And electrons, the 10,000 times lighter guys, they are basically running around crazy around these are electrons. Okay, so electrons are very mobile, they are very lightweight, so they are basically running around at a very fast speed, okay, around the nucleus. So this is how atoms look like. Okay, atoms look like, you have a small nucleus in the middle where you have your protons and the neutrons, and then electrons are running around crazy around the nucleus. Okay, around the nucleus. So that is how an atom looks like. Even though this looks like, I mean, this is nothing compared to a sphere, right? So atoms are not solid spheres. Okay, the atoms are not solid spheres. In fact, they have a more dynamic structure. And also the actual structure is even different than what I showed you. Okay, so nucleus is actually very small. Nucleus is where you have the protons and neutrons. Okay, and the nucleus is actually very small. Okay, it is like a tiny dot in the middle of an atom. Okay, even though it contains the big heavy protons and neutrons, it's like a tiny dot in the middle. Okay, and then majority of the atom is basically the electron cloud. Okay, electron cloud, which is basically this area. Why did I say it's the electron cloud? Because that is where you can find your electron. Remember, electrons are not going to stay in one place. Okay, they are running around. So basically electrons are running around in this area. Okay, so you can find your electron in this particular area. Okay, let's call it electron cloud. Okay, electron cloud. Okay, so that is how atoms look like. So let's summarize what we learned. Okay, we learned something really important. Okay, so in an atom you have three subatomic particles, like protons, neutrons and electrons. Protons and neutrons, they are heavy and approximately equal in mass. Electrons are much lighter, and they are basically 10,000 times lighter than the mass of a proton or a neutron. And then the other important thing that we learned is that they are charged. Protons are positive, neutrons are neutral, okay, and then electrons are negatively charged. That is something that we learned today. And then also the two heavy subatomic particles are going to be concentrated into the center of the atom. We call it the nucleus. Okay, we call it the nucleus. Protons and electrons are going to be centered or concentrated into the middle of the nucleus. We call it the nucleus. Okay, and then the electrons are basically running around this nucleus. Okay, we call it the electron cloud. Electron cloud is the location where we could find our electrons running around. Okay, and let me ask you this question. Why do electrons, I mean, they have very high energies, they are running around at very fast speeds, but why do they stick to the nucleus? Why don't they just go away? When you have so much energy, you can just simply they can simply leave the nucleus, right? Why do they running around? I mean, why do they moving around the nucleus? Why do you think? Because of the charge, of course. Because of the charge. You know, nucleus has positive protons. Okay, so basically nucleus has positive protons. So nucleus is positively charged, even though neutrons are not charged. Okay. Nucleus is positively charged because of the protons, and then electrons are negatively charged. And then these two are attracted to each other through electrostatic interactions. Negatives and positives attract towards each other through electrostatic interactions. So that is why, even though electrons have high energies, they are not going to leave the nucleus easily, because they are attracted towards the nucleus. Okay, keep that in mind. Okay, so that is why all this dynamic structure is possible, because electrons are attracted to the nucleus of an atom. And here's the other thing. Okay, so now we know the three subatomic particles, their charges and their dynamic structure. Now let's talk about the number of each subatomic particle present in an atom. Okay, so atoms are neutral. Okay, remember that atoms are neutral. Okay, even though it has charged subatomic particles, overall atoms are neutral. So if you want to make something neutral by using two different opposite charges, I mean, if you want to make something neutral by using positive and negative charges, how do you do that? Let's say charge of a proton is equal to the charge of a electron, but of course they are opposite. Okay, how do you make the overall atom neutral by using protons and electrons? You have to take them in equal amounts, of course, right? So you take equal amounts of protons and electrons. That is how you do it. You take the same number of protons as compared to same number of electrons. When you have the same number of negative charges and positive charges, they cancel out each other. And then the overall atom will be neutral. Okay, so the number of electrons should be equal to the number of protons. So the positive charge will be equal to the negative charge. And then of course the overall atom is going to be neutral. All right, so that is the first thing that I want you to remember. Number of atoms, number of protons of an atom is equal to the number of electrons. And then let's move to the next slide. And this slide is actually very important because even though it is just one slide, it contains a huge amount of details. Okay, it contains a huge amount of details. So you might want to, review this video multiple times. Okay, we can review this video multiple times and try to understand this. Okay, this is a very important slide. Okay, so once again, guys, all of the subatomic particles are extremely small, of course, and contain very minute masses. And of course, protons and neutrons are heavy. Electrons are 10,000 times lighter. So their mass, electron mass, is negligible when it comes to the mass of a proton or an electron. Okay. So now we are going to talk about two numbers. Okay. Atomic number and mass number. Okay. We are going to talk about two different numbers. Okay. I'm going to skip a couple of bullet points and then I'm going to start discussing two things called atomic number and mass number. Okay, so atomic number is basically a number that represents the number of protons in an atom. Okay, atomic number is basically the number of protons in an atom. Okay, so if you take a look at the periodic table, okay, every element is going to have an index number. Okay, hydrogen is going to be 1 and then helium is going to be 2, like that. So every element has an index number. Okay, so this index number is actually the atomic number. Okay, so this atomic number is equal to the number of protons in an atom. Okay, so in the periodic table you have many different elements. Okay, so these elements are arranged according to an index number starting from 1, okay, and increasing by 1. Okay, when you move from one element to the other, okay, they increase by 1. Okay, so this index number is known as the atomic number. And the interesting thing about this atomic number is that the atomic number is equal to the number of protons in an atom. So no two elements are going to have the same atomic number. Okay, no two elements are going to have the same atomic number, and this atomic number is equal to the number of protons. So no two elements are going to have the same number of protons. Okay, if you take an example, okay, let's take hydrogen and helium. Okay, these are two elements next to each other in the periodic table. Okay, hydrogen atomic number is number 1, so therefore hydrogen has 1 proton, and then helium atomic number is number 2, so helium has 2 protons. Okay, so no two different elements are going to have the same number of protons because the atomic number, the index number, is equal to the number of protons in an atom. Okay, So here's the thing. If the number of protons is known, if we know the number of protons, which is basically equal to the atomic number, we know the number of electrons in an atom, right? Do we know it? Of course we know, because they are equal. Protons and electron number is equal, right? So we know that number of protons is equal to the number of electrons. So basically atomic number gives you the number of protons and also the number of electrons, because they are equal. Right? Okay, so that is atomic number. And then the next number that we are going to talk about, okay, is called mass number. Okay, is called mass number. Here's the thing. Mass number has something to do with mass, right? Of course, that is why it says mass number. Right, so when it comes to the mass of an atom, of course, the mass of electrons are insignificant. So only mass subatomic particles masses that matter are mass of a proton, and mass of a neutron, right? These are the only two subatomic particles that matters. Okay, mass of a proton and mass of a neutron. So mass number only depends on mass of a proton and mass of a neutron, or in other words, number of protons that you have and the number of neutrons that you have. Number of protons that you have and the number of neutrons that you have. Okay, these two numbers will basically give you the mass number. Okay, mass number. So let's talk about it in more detail. All right, so for any element, okay, let's take helium for an example. Okay, that is the same element that you have in your slide. Okay, let's take helium. Okay, so let's take helium. When you take helium as an example, it has an atomic number. Which is 2, of course. That is the index number. You read it from the periodic table. And let's say it also has 2 protons. Okay, it also has 2 protons. How do you know that? Because it is equal to the atomic number. It also has 2 electrons. Okay, and how many neutrons it has? Okay, it could have let's say it has 2 neutrons. It could be different. Okay, it could be different, but for this example, let's say it has 2 neutrons. Okay, so let's say you have taken an atom, a helium atom, and it has 2 protons, 2 electrons and 2 neutrons. Okay, so what is the mass number? What is the mass number of this helium atom? I mean, you just simply have to add the number of protons and neutrons. So the mass number will be 4. Okay, so this symbol that I just drew, okay, we call it the atomic symbol. Okay, remember, this symbol is for atoms, not elements. Okay, so this symbol is called atomic symbol. This symbol is called atomic symbol. An atomic symbol basically has the atomic number as a subscript. So this is the atomic number. And of course the mass number. It has the mass number as a superscript. Okay, superscript. So that is called atomic symbol. Of course, this is a symbol for atoms. Okay, so let's take another symbol. Let's talk about carbon. Okay, let's talk about carbon. Let me use a different color. Let's talk about carbon. Okay, let's say carbon has an atom. Okay, and carbon atomic number is 6. If you take a look at the periodic table, the index number for carbon is 6. So this is the atomic number for carbon, and let's say the mass number for carbon is 12. Okay, so by looking at the symbol, okay, this is an atomic symbol for a carbon atom. You know that it has 6 protons because that is the atomic number, and it has 6 electrons because number of protons is equal to number of electrons in an atom. And how many neutrons does it have? 12 minus 6. 12 is our mass number. You subtract the number of protons out of it, so you get 6 neutrons. Okay, you get 6 neutrons. Okay, so that is how you calculate the number of neutrons. So let's take another carbon atom. Okay, so since it is carbon, it has to have the atomic number of 6. Okay, and then mass number is 13. What did I do here, right? So can I do that? Of course I can. Remember, you can have atoms of the same element. With different mass numbers. We call them isotopes. Isotopes. What are isotopes? They are atoms of the same element. How do we know that they are atoms of the same element? How do we recognize them as the same element? Of course, the elemental symbol is carbon. Okay, element symbol is carbon, and also the atomic number is 6. Okay, the atomic number is 6. So we know that they are both carbon atoms. But here's the thing, the only difference is that they have a different mass number. They have a different mass number. So isotopes are atoms of the same element with two different masses. We call them isotopes. Why do they have different masses? They have different masses because they have different number of neutrons. They have different number of neutrons. So both these carbon atoms, of course, both these carbon atoms have 6 protons. That is the atomic number for carbon. Okay. And then 6 electrons. But if you calculate the number of neutrons for the second carbon atom, carbon 13 atom, okay, it has 13 minus 6, which is 7 neutrons. It has 7 neutrons. So as you can see, for these two isotopes of carbon, they have two different numbers of neutrons. Does it change the charge of carbon atoms? No, because neutrons are neutral, so they don't impact the charge of an atom. Atoms are still neutral. You have 6 protons, 6 electrons. Protons and electrons are the only things that impact the charge of an atom, right? So both these atoms are neutral because protons and electrons are unchanged. But of course, you have increased the number of neutrons, or you have changed the number of neutrons in these two atoms. When you are changing the number of neutrons, they are neutral particles, but of course they are heavy neutral particles. So therefore, their masses are different. That is why the mass number is changing. That is why the mass number is changing for these two carbon atoms. Okay, we call them isotopes. We call them isotopes. I hope you are clear. All right, so isotopes are atoms of the same element with different number of neutrons, or in other words, with different masses. So basically, I mean, now we know all atoms are not identical, right? They have the same number of protons and electrons, okay? But sometimes atoms of the same element could be different in mass. It's like, you know, two identical twins, okay? Isotopes are like two identical twins, okay? They have the same nose, same eyes and everything. But of course, let's say the two isotopes have two different food habits. So therefore, one twin is bigger than the other. Okay, one twin is bigger than the other. So one is heavier than the other. So mass is not identical. So those are isotopes. So isotopes are like two identical twins, but with different food habits. So one is bigger than the other. Okay, one is bigger than the other. They are both identical. Okay, they are both the same element. Okay, they come from the same element. They have the same number of protons and electrons, but of course they have different number of neutrons. All right, and the next thing that we are going to talk about is atomic mass unit. Okay, atomic mass unit. Why do we need a different unit? Why do we need something like an atomic mass unit? You know, subatomic particles are very small. Okay, even the heavier subatomic particles like protons and neutrons, they had masses that are very small. Okay, which is basically 10 to the power minus 24 grams. Okay, 1.7 times 10 to the power minus 24 grams. So they are very small in mass. I mean, gram is a very small unit. Okay, so still this unit is much bigger when you are measuring the mass of a subatomic particle. So it is much bigger. So you can't use grams. The scale is very big. It is like, you know, measuring the length of a bacteria using a meter ruler, or measuring the length of a bacteria using a yard. Okay, it's too big. Okay, so what chemistry people or science people do is that they define a new mass unit called atomic mass unit. Okay, we call it AMU. Okay, so AMU is basically 1/12 of the mass of a carbon 12 atom. Okay, so AMU is defined AMU is defined as 1 AMU, 1 atomic mass unit, is equal to 1/12 of the mass of a carbon 12 atom. Okay, what do we know about carbon 12 atoms, guys? What do we know about carbon 12 atoms? Okay, carbon 12 atoms have 6 protons, 6 neutrons, and of course 6 electrons. But when it comes to masses, I mean, the AMU is a mass unit, so we talk about the mass, right? So electron mass is insignificant, so let's scratch it out. So carbon 12 atom, okay, has 6 protons and 6 neutrons. That matters for the mass, right? So 1 AMU is 1/12 the mass of a carbon 12 atom. Rather than calling it like that, you can rewrite this using protons and neutrons. So you can say it is 1/12 mass of 6 protons plus 6 neutrons. Am I correct? Am I correct? Yes. Because electrons doesn't matter. Carbon 12 atom is what? 6 protons, 6 neutrons, right? Basically, when it comes to mass. So you can say, you can rewrite this as 6 times mass of protons plus 6 times mass of neutrons. Are we good? Of course. And you know that mass of a proton is approximately equal to the mass of a neutron. So we don't have to maintain MP and MN, which stand for mass of a proton and neutron. We can just simply use one type, right? So rather than using MP and MN, we can convert these 6 N's to what? 6 N's to 6 P's, okay? Because their masses are equal. So 6 masses of protons plus 6 masses of protons, we can say it is 12. Okay. So what is 1 AMU? 1/12 times 12 mass of a proton. Okay, so 12 times the mass of a proton. Okay, our assumption is, of course, mass of a proton is approximately equal to mass of what? Mass of a neutron. This is our assumption. And then, as you can see, 12 to 12 will cancel out. Okay, so 1 AMU is what? 1 AMU is approximately mass of a proton. Okay, so we are going to measure the mass of an atom. Okay, mass of an atom approximate to the mass of a proton. Okay, so this is how it does. Okay, this is how it happens. So basically AMU is very similar to mass number. Am I correct? Yes, AMU is very similar to mass number. What is mass number? Mass number is the number of protons and number of neutrons, right? So basically AMU is very similar to mass number. Okay, so AMU, atomic mass unit, is a very small unit of mass that is defined by scientists to measure the mass of subatomic particles, and approximately 1 AMU is equal to the mass of 1 proton, or you can say the mass of 1 neutron. Okay, remember, it is approximate, it is not certain. Why? Because if you want an exact value, 1 AMU is actually 1/12 mass of a carbon 12 atom. Okay, carbon 12 atom, you take 1 carbon 12 atom mass, which contains 6 protons, 6 neutrons and 6 electrons, and that mass is actually 1 AMU. Okay, so if you measure masses in 1 AMU, if you measure masses in AMU, mass of a proton or neutron is approximately 1 AMU. Okay, and mass of an electron is very small, 10,000 times lighter, so it is very close to 0 AMU. Okay, it is almost insignificant. All right, so we talked about so many things in this slide. We talked about the atomic number, we talked about the mass number, okay, and then we defined a new mass unit called AMU. Okay, and We also talked about a concept called isotope, or a term called isotope. Okay, so we learned the atomic symbol, so many things, right? So the last term that we have left, okay, is called atomic mass. Okay, the last term that we are going to talk about today is called atomic mass. We didn't discuss this thing yet. Okay, so if you take a look at an element in the periodic table, okay, let's take helium for an example. Of course, you have the index number, which is our atomic number. So this is our atomic number, we know that. And then also there is a decimal number for every element. There is also a decimal number for listed or written on the periodic table. So this number is usually approximately twice, I mean it is not always the case, but it is somewhat close to twice the atomic number. Okay, this decimal number is actually known as atomic mass. Okay, atomic mass. What is atomic mass, you ask me? That is the average mass of an atom. Okay, average mass of an atom for a particular element. So wait, I mean, we thought that every element has the same type of atom, right? No, it is not. We just learned that elements have isotopes. Okay, atoms with different masses, even though they have the same number of protons and electrons, they have different masses. So atoms could have isotopes. So atomic mass is the average mass of an atom. Okay, you get all the identical twins, you average the mass. Okay, it is like, you can imagine elements such as different species. Okay, you can say one element is humans, the other element is dogs, another element is cats. So different species of animals are different elements, let's say. So if you want the average mass of a human, which is one element, you have to measure all the masses of every human and then divide it by the number of humans in a population, and you get the average mass of a human, right? So let's say we do that to our class. Okay, our class might have skinnier people, bigger people, but if you want the average mass of a human in our class, we take masses of every student and then we divide it by the number of students. So that is how you do the atomic mass. Okay, that is the average mass of an atom. Okay, average mass of an atom. So to do that, you could have smaller isotope, I mean less heavy isotopes, heavy isotopes. So you add the masses up and then divide it by the number of atoms, you get the atomic mass. Here's the thing, to calculate this you need a couple of different things. You need to know the type of isotopes of that particular element. Okay, and then you need to know the relative abundance of a particular isotope. Let's say an element has two different isotopes, a light isotope and a heavy isotope. Of course, they are going to be different in masses. One is heavy, one is light. Now let's say this particular element has majority of lighter isotopes as compared to heavy isotopes. So the average mass will be a little bit light, right? Because the population, relative abundance of each isotope matters. Okay, it is like, in a class, if you have more larger people as compared to smaller people, then the average mass of a student in a class will be high because you have more heavier people, right? So like that. So atomic mass is basically the average mass of an atom, and it is approximately the number of protons and neutrons. Okay, it is approximately the number of protons and neutrons, but here's the thing, different isotopes have different number of neutrons. So that is why this is always a decimal number. Okay, it depends on the relative abundance of different isotopes. Okay, and we will do a simple math problem in a future slide, and you will understand this concept better. Okay, so hang on tight if you didn't get it completely now. Okay, about how to calculate the atomic mass, we will do a small sample problem later on. Okay, all right, so that is all I want to talk about in this slide. So let's do some sample problems and then see if we can hone our skills. Okay, all right, hang on tight. Okay, because most of the times people are a little bit confused after this slide, but once we do the study checks, it becomes much clearer. Okay, so here's a sample problem. Okay, identify the subatomic particles that has the following characteristics. So this is what you will do. Okay, you will pause the video and then see if you could try this sample problem by yourself. Okay, so name 3 subatomic particles for these 3 questions. Okay, all right, so pause the video and see if you could get the answers. All right, let's discuss this. No charge. What subatomic particle has no charge? It's the neutrons, right? Neutrons have no charge. Okay, so the answer is neutrons. What is the subatomic particle that has a mass of 0.00055 AMU? Okay, so that is a very small subatomic particle or very lightweight subatomic particle. We know that a proton is approximately 1 AMU. Okay, a neutron mass is approximately what? 1 AMU. And this mass is what? A much lighter mass. So that must be electrons, right? That must be an electron. Okay, if it is a proton or a neutron, it should be 1 AMU. So this is about 10,000 times smaller than 1 AMU, right? So that should be an electron. A mass about the same as a neutron, is what? A proton, excuse me, a proton. All right, a proton. So these are our answers. Okay, I hope you got it correct. And here's another study check, true or false. Is the following statement true or false? You might want to pause the video whenever you want to answer the questions without me explaining them to you, okay? Pause the video. Feel free to pause the video. And the nucleus occupies a large volume in an atom. That is definitely false. Even though nucleus contains big, heavy subatomic particles, the size is much smaller. Okay, it is less than 1%. Okay, less than 1% of the size of an atom. Okay, it is tiny dot. It is a tiny dot in our atom. So that is definitely false. That is definitely false. All right, using the periodic table, state the atomic number of protons and number of electrons of an atom of each of the following elements. Okay, so here we wanna I have given you 3 different elements. I want you to tell me the number of protons. First of all, I want you to tell me the atomic number of protons and number of electrons. Okay, so let's see if you could do it. All right, let's see if you could do it. All right, so the first element, you might want to pause and answer. Okay, first, but here's the thing, atomic number is equal to what? The number of protons. The number of protons is equal to what? The number of electrons. So all you need is to figure out the atomic number, right? So for nitrogen, what is the atomic number? How do you know that? Figure out the index number for nitrogen, which is 7. So nitrogen has an atomic number of 7. So the number of protons should be 7. Number of electrons should be 7. Magnesium, the atomic number is 12, so the number of protons are 12, number of electrons are 12. Bromine, the atomic number is 35, so the number of protons are 35, number of electrons are 35. Very straightforward. Am I correct? All right, so here are your answers. Okay, and then let's try to do this study check. Consider an atom that has 79 electrons. Okay, of course, if you have 79 electrons, how many protons you have? You have 79 protons. Okay, so if you have 79 protons, what is the atomic number? 79. Okay, 79 is the atomic number. So you look at the periodic table, find the index number 79 and figure out the element symbol, which is AU. AU. You might want to do this by yourself. Okay, you might want to do this by yourself. Here's another very nice study check. You might want to pause and try it before I explain it. And this study check is from isotopes. Okay, it's from isotopes. Okay, so in here you have 3 isotopes of neon. How do you know that it's neon? Of course, the element symbol is Ne, and if you take a look at the atomic number, it is 10. Atomic number is never changing, okay? Index number is not changing for neon, so atomic number is not changing, which means the number of protons and electrons are not changing for neon, okay? So you need to find out the number of protons, neutrons, and is that it? Electrons. Let's throw in electrons as well. So you need to figure out the number of protons, electrons, and neutrons. Very straightforward. So protons, number of protons is equal to 10 because it is the atomic number. If you have 10 protons, you should have 10 electrons. So for all these three isotopes, you have to have 10 protons, 10 electrons, 10 protons, 10 electrons. Neutrons, okay, how do you figure out the neutron number? You take the mass number, which is 20. Mass number is the number of protons and neutrons, and you subtract the number of protons, which is the atomic number, which is 10, and 20 minus 10 is what? 10. For 21, neon 21, so you subtract 10 from 21, and the number of neutrons is what? 11. And here the number of neutrons is what? 12. Okay, so those are the three isotopes that you have. Okay, so each isotope has different number of neutrons, but number of electrons and protons remain the same. Okay, this is how we do the math. And our last sample problem for this video is about calculating the atomic mass. Okay, this is something important. Okay, so you might want to study this slide well, because most people have trouble understanding atomic mass. Atomic mass is basically what? The average mass of an atom. Okay, you have to calculate it. How do you calculate it? To calculate it, you need isotopes, all the isotopes of a different, all the isotopes of an element, and then you need the relative abundance, okay, or percent abundance. Okay, so we have a calculation regarding to magnesium. Of course, magnesium atomic number is 12. Magnesium atomic number is 12. So magnesium has 12 protons and 12 electrons. 12 electrons. This much is clear to us. Okay, so all three isotopes of magnesium has 12 electrons and 12 protons. We know that. Okay, and let's talk about the three isotopes. Okay, and their mass numbers must be different. Okay, and you can of course calculate the number of neutrons by subtracting the atomic number from mass number. Okay, and they are also nice enough to give us the mass of an isotope, which is the AMU. Okay, AMU is basically equal to the mass of a proton. So basically mass of an isotope in AMU is actually very close to the mass number. Okay, as you can see, mass in AMU is actually almost the same as the mass number. Why is it slightly different? Because mass number has mass of a proton and mass of a neutron, and of course we made the assumption that they have the same mass or almost the same masses, but they're slightly different. And also we don't consider electron mass, right? So those are the things that factor into this small variation in AMU and the mass number. Okay, but if someone don't give you the AMU, it's okay, just use the mass number. That is almost the same. Okay, that is almost the same. I hope I made myself clear. All right, 1 AMU is what? 1 AMU is approximately mass of a proton. So if you have certain number of protons and neutrons, that will be equal to the mass of that isotope in AMU, right? So the other thing is percentage abundance. Okay, what is the percentage of each isotope in that population? Okay, so when you add these three up, it should be 100%. Okay, all right, so we have that, and then let's try to calculate the atomic mass. So here's what we do. We try to take all these three isotopes, and then we take the AMU value, or if you don't have it, you can use the mass number, and you multiply it by the percentage abundance. By doing that, we calculate contribution to the atomic mass from each isotope. Okay, so if you have a higher percent abundance, if a certain isotope has a higher percent abundance, like this one is 78%, more than 3/4 of abundance comes from magnesium 24, so the contribution is high. But of course magnesium 25 and 26, they have smaller abundances, so their contribution to the atomic mass is small. Okay, so you take the percentage abundance, you multiply it by the mass number or AMU, and you get the contribution to the atomic mass, and you finally add them all up, and that will be the weighted average mass. Okay, that will be the atomic mass of magnesium. That will be the atomic mass of magnesium. All right guys, with this I'm going to conclude this video. Just let me know if you have any questions. Okay, just let me know if you have any questions, and please feel free to go back and listen to this video again and again if you have any questions. You guys have a good one. Okay, take care.